Alright, hello world. Um, so I'm back. I might be stumbling through this today because I'm a little tired and I haven't looked at this since Thursday or whatever. Um, we actually had done 34.1. 34 is an easy one. It's pretty straightforward. Most of these require some little trick. Like 31 is an easy one. 31.1 is pretty trivial. And then, if I recall, I think he did 31.2 just by induction. I would have thought there was some sort of trick to that. 32 and 33, it's like, I guess if you look at the right hand side and you want to come up with a series that would have that as a coefficient, as like your typical binomial coefficient. That's like a hint at it. This is basically, like 32, it is just basically a square of your typical series that you might expand with a binomial theorem. But for some reason, when I first saw that, I was like, well, how am I going to deal with the cross terms? But you're looking specifically at the nth coefficient. So all of the cross terms, well, it's not a trick, but like the cross terms end up being like n0 and n, and n1 and n minus 1, and n2 and n minus 2. So like they all happen to be equal, and that's why you're getting squares. That's for that particular coefficient. And then anyway, like I was saying, 34 is really pretty trivial. That's just what happens when you multiply two series together. So he's telling you that this would be the formula for the product. And then if you have factorials in your denominator and you have factorial in your product, then you get a different formula that involves the binomial coefficients. Kind of looks like the binomial theorem again. And 34.1 did involve a trick. So 34.1 is where we ended last time. Like, I was just staring at it and I wasn't sure how to do it. But it's really easy if you sort of realize it's coming from this second definition, and you could just multiply by e to the x. Your alphas would be 1 in that case, right? So I probably shouldn't bring it up again because we talked about it last time, and I don't want to make this video too long today. But at the very end, I had gotten confused, and there's really no reason to. It's pretty straightforward. So it's saying if your bn's are defined like this, the sort of alternating series with binomial coefficients of some given a's. First of all, another way to phrase this hypothesis is like, suppose you had a series like it's going to write just bn, x to the n. But now that I think about it, you probably want it to be, you probably want it to be like bn over n factorial x to the n, right? And we'll let ax be the same thing, something like this, right? Starting at 0, and it doesn't actually have to stop. It can just go off to infinity, I suppose, right? For a particular one, for Bn in particular, it's a finite sum, but the series is not necessarily finite. Anyway, so if you use this terminology, you can also use the e to the x function, which is just 1 over, right? So by 34.0, when you multiply two series that have a factorial on the bottom like that, like for instance e to the x, your gamma value is going to be given by this formula, which is conveniently almost exactly what they gave us here, except for the alternating bit. Okay, so yeah, it's not. Here's another way to express how the BNs are defined. I think this is his first step. Is he's like, well, if there was an alternating term in addition to your actually, I guess I must have this backwards, huh? Let's put an A here, AK. Like Z to the K. Oops. Let's do Z, since I just switched it up. Then this would give you a new number on the right, which is really just 1 times this, yeah, with the binomial coefficients in between. So we could put over here like B sub K, K factorial, C to the K. And that would define the BNs. Like we know from 34, we have Bn is the product of whatever this is. Of course, it's 1. Let me pull that up again. But it's just, alpha 0 Bn plus, then you get this binomial expansion type of thing for the coefficients. And it changes in a pretty predictable way, right? So the sum is always n. So here you might have 1 times and then this thing at 0, which I guess would just be a0. And then you get a negative sign for the first guy, right? Negative 1 to the 1, a1, and that's times 1. Like the coefficient from this E series is always just going to be a 1, so it's not really doing anything interesting there. And I forgot it already that there's supposed to be a term here, right? So if you're doing this in n, you should have an n choose 1 right there, okay? It really just follows from the first part, along with the extra factorials. So when you multiply by one of the factorials, it kind of becomes this formula, n factorial over 1 factorial times n minus 1 factorial. So it just follows from the Cn part. So yeah, we're getting stuff like this, etc. So negative 1 to the n choose n, I guess an, and then you're getting whatever this guy is, but it's a 1 all the time, so it's not super interesting. So that was the hypothesis. Like if Bn is defined this way, then you want to show that An is also basically defined that way. Like you're going to get B0 minus N1, B1, up to negative 1 to the n choose n, Bn. Like show that happens. But so this was the whole trick, is like defining B in this manner using this product makes it really easy. For some reason I was like, I still don't get it, and I was trying to multiply by e to the negative z, which is almost the right direction. You can basically just replace z with negative, like take this almost as an identity, because that's the definition of the BNs, right? Replace z with negative z. And you'll get e to the negative z on this side, but we're going to move it over here. So you'll have e to the negative z times the sum, negative 1, AK, and I'll put a negative z here, okay? So the negatives are going to cancel, and you're just getting, and this still equals on this side, but now it's got this alternating bit, right? Because we replaced it with negative z instead of z. So if you move the e to the z to the right side now, you've got exactly what you wanted. Okay, and on the left, these two canceled, so you actually just get AK on its own. And that is exactly what we were trying to show, that if this happens, then it sort of happens going the other direction as well with the bn's. So now your AK is given by this alternating formula that we jotted down a second ago. You know, very much like the bn was defined in terms of the an's a moment ago, or the AKs, I should say. The an is defined in terms of the bk's in the same exact manner. So it's really the kind of a trivial change. Once you notice this trick of multiplying by the series e to the z, anyway, we saw that last time. So what I wanted to do today, I have done 35, but I didn't do 36. Like, it's just over my head. I'm going to read the explanation. I don't think I'm going to even try it. I'm just going to try to understand it. And I haven't done any of the other ones, so it would have been smart for me to prepare. Like, 40 looks familiar to me, but I don't remember where I would have seen it. The other ones don't really look familiar. This one's interesting. You get this harmonic sum. Yeah, I'm not familiar with that one either. So I have not seen any of these before. Oh, sorry, my gain is way up. I haven't seen any of these. Probably be smart of me to prepare for the next video, but then I don't know. Maybe it's less interesting. Anyway, I did do 35 at some point. I think he does it in a more clever way than I do. I don't remember what he does, but he does something really. He just makes some observation that makes it fast. I didn't do it that way. I think you can do 35 with induction. So that is what I had done. So let's take a look at 35. He defines this new operator, x to the n given h. And it's very much just your typical factorial thing, except that instead of going down by 1, we're going down by h. Okay, so we take n factors where you decrease by h every time. Right? Here'd be a 0 factor, a 1 factor, 0 through n minus 1. So you get n total factors of things that decrease by the amount h. And then he tells you you have this identity, which is basically just the binomial theorem again, but with this new operator. So that's wild. Like, basically the binomial theorem holds even if you had redefined factorials to not be by integers, but by any real number h. So that's impressive. So the way I did this was I just noticed, like, first of all, x to the, like, well, I guess for instance, x to the 1 given h is an x. Okay. And then yeah, I'm looking at 35. And then I started, like, probably playing with what this would be to different powers. So, like, of course, one of them is just itself, like we just said. But how do you get from 1 to 2? Like, what is 2 given h? I guess it's like itself times x plus y minus h. So you can kind of group this minus h term with either one, whichever it's more convenient for you to do, you know? what we're supposed to be observing is that you get this binomial. Well, first of all, notice that it's true for 1. This is the case of n equal 1. Notice that you're getting x to the 1 h plus y to the 1 h. So it was true just for n equals 1 case. For 2, though, I'm multiplying by this thing. Like, of course, we're going to distribute, but let's see. Yeah, there's an extra y, right? Like, we can group the h with whichever variable it's convenient for you at the time. So like one time this hits against x, and it's probably going to be convenient for me to take x minus h, right? So one thing you get is x times x minus h plus y, and then the other one you get is y times like that. You get both of those terms. This term right here looks like x to the, not 1h, but I guess 2h, right? Plus y 1h, and then here I've got, oh, wait a minute, that's not true. That's y1h times x. So it's like x to the 1h times y to the 1h. And then over here I've got y to the 1h, x to the 1h, plus our y 2h. So it seems like it worked. N is 2 in this case, and we're getting, sort of 2 choose 0 plus 2 choose 1 times this term. So it obviously worked for n equals 2 as well. And then here we got 2 choose 2. So I figured, it took me a minute, but I did it by induction the other day. After I noticed that this happened, I was like, well, it probably happens in general. So if you knew that it happened for n minus 1, could you get there? Like, could you take n minus 1 h and multiply by x plus y minus, I guess it would really be this, right? And do you get, like, basically show that you get the formula for x plus y to the nh. Okay? Our n choose k as k goes from 0 to n of x to the I suppose it would be, you could go either direction. Let's do n minus k given h times y to the k given h, right? So I'll be looking to show that this occurs if you know that it happens for this factor, proof by induction. So I was trying to do induction on n. That's what I would do on this. That's just because, like, again, I noticed that it happened. Like, I noticed that it fell out for the case of 2 in kind of a cute way where I could, like, group them. So I was like, well, it probably can't be that bad to do it by induction. So here we're assuming that it's true for this case. I mean, I already saw that it's true for 1 and 2. But now we're assuming that it's true for n minus 1. Knowing that this part can be expressed as a sum of n choose k, x to the n minus k h, y to the k h, as k goes from 0 to n. And then we're going to multiply this by the next term, the last factor, I should say, in your definition of this little creature. So yeah, again, this would be n terms. That would be the last factor. There's, I should say, n factors, starting at just x plus y minus 0h, x plus y minus a single h, times down to this x plus y minus n minus 1 h's. So my goal would be show that this equals this, or in other words, now that we know that this if you believe this left-hand side is given by this formula, does this times this factor equal this right-hand side? So show that this equals this right-hand side. Did I screw this up already? I did, right? Because because this is not n minus 1. So let's change this to do it correctly. That might make your life a little easier. This top part is not an n, it's supposed to be an n minus 1. So this is x to the n minus 1 minus k given h. See, I told you I was tired. Anyway, this would be the n minus 1 case. And now we're able to I'm thinking, of course we want to replace this with n choose k somehow, but we do know that n choose k is the same as n minus 1. You can do this with it, which we had just shown back in number 31. A few different ways to believe that. You can't even see what I'm writing anymore. So yeah, I would probably expand this, right? So we get two different, like the left-hand side, I haven't done anything yet. I'm about to replace this n minus 1 choose k with probably like this minus that was my instinct, you know? But I might be wrong. I don't, you know. That's what I chose to do. This has not changed. This is still n minus 1. And then this is our left-hand side. I'm still trying to multiply this whole thing by this one term. So I'm claiming that that's going to work out for you. Like, if we do this out, it'll somehow equal this stuff. Looks like the 0 term here is going to be meaningless. Like, one of these will drop out. But then when you get to... I was going to say we want to reindex this second term. First term, maybe we'll just remove that 0th term. Here, let me pause for a sec. All right, back. So if you're just popping in, this has been kind of a sloppy start. But it's kind of a cool problem. I wonder what wonder what other, because he doesn't seem to be using this thing anywhere. I wonder if this has any applications, this operator. Yeah, I don't see him using it. But yeah, let me recap since I need to rewrite this anyway. So yeah, the question is, he's defined this new operator. It's a lot like a factorial, but instead of being decreasing by 1 on every factor, you're decreasing by h, just a real number h. So if you have n terms, that means it looks like this, right? And then we're going to have n of these terms, like that. One thing I noticed right away was that if you let n be 1, you'll just get x back. And then what he's asking us to show is that you basically have the binomial theorem again. If you were to expand this under this definition, it works out to be this stuff. So like the sum of the first argument is always n, just like with exponents, the sum is always n in the binomial theorem. And other than that, you get binomial coefficients as well. So we're trying to show that x plus y raised to this, this operator will actually give you, I realize it's right here, I don't need to think about it, but yeah, the first term is like n given h, and then you get n choose 1, and then this goes down by 1, and you've got a single y there. Oops, that's an h, damn it. Anyway, you get the idea. X to the n minus 2 h, y to the 2 h, all the way up to n choose n. I guess this one will be y to the n h, and x to the 0 h, which would be 1 times nothing, 1 times 1. So I'll show that this happens. And I noticed that it happens sort of obviously for 1. I mean, it happens like this is x to the 1h plus y to the 1h. So I noticed that it happens for n equals 1 case. But it even, like if you multiply this guy by x plus y minus h, it'll group either direction. So it works for, it's true for n equal 1 and n equal 2. I don't know why I'm writing this out again for you, but so for instance, this would be I mean, it's this by definition, right? But when you expand that, you get x1h times y. Yeah, I was saying a moment ago that you can group it different ways. Like when you multiply by this term, you can group the x with x minus h, and you can group the y with y minus h. And so that formula does kind of naturally pop out. So like when you do this, this is just the n equal 2 case, like my base case for induction here. When you do this, you can group the x with x minus h, and you can group the y with y minus h. So you're getting x2h plus xy. I'll just write it as xy for now. And then over here you get another xy, and you get y2h. Right? Two factors where you decrease by h. That's the y times y minus h part right there. And so in between here, we happen to have 2 choose 1 times x to the 1h, y to the 1h. I know I didn't really need to rewrite all this. I just thought, why not start over? Why not waste some more ink? Yeah, so it's true for 2 as well, right? You're seeing that happen. This is the first time, and it's kind of interesting that you get a 2 there. So let's suppose we know for n minus 1 that we have this happening, that we have a formula for it that goes n choose k x to the n y to the k, like that, and this goes from 0 to n minus 1. So yeah, suppose we know that our formula is true for the n minus 1 case. We want to show that it's true for the n case. And I was like, of course, to get from here to there, we know what to do. We just multiply by this term, except it's not minus h this time, it's minus n minus 1h. So we know this is by definition. You just multiply this by x plus y minus, and this time we'll have n minus 1 h's, whereas this guy sort of contains n minus 2. That's the last factor that it has, is n minus 2 times h. But yeah, if you multiply this by this, you will get that. That's just the definition of this thing. And we know that this chunk here is given by this formula. So anyway, this is where we were on the other side of the sheet. This is where I had just stopped and said, I'm taking a break and I'm gonna rewrite things. And I feel like you want to just use, you can exchange this with you can exchange this with this junk I was saying. You can use this identity. Pretty sure that's going to be the whole point. Like, that's going to be what makes this work. So I'm going to use the fact that, so let's see, I know this is true, same as this, and like, I also know that when you, like, I can, when this thing gets multiplied by x minus n minus 1h, it increases this exponent by 1. Same thing with the y. Well, hold up. Not exactly true with the y. You gotta be a little careful. But we can introduce a term here, I suppose, right? Yeah, it's not exactly true here because there's a k. So we're gonna need to split this up, like, can I do something like minus k plus k? Grrr. Yeah, you see what I was saying? Like, if k was 0, then part of what I was saying was true, but it's not 0, it's some integer. So you're going to want to, like, subtract kh and add kh, basically, inside this factor to make it happen. And my ADD is telling me I should just show you the answer because it's going to be much easier than what the hell I'm doing right now. But let's not do that. So yeah, my brain is screaming at me to write minus kh plus kh in here to help start grouping things, but anyway, we can get this all on one page if I say recall that n choose k is the same as n minus 1 choose k plus n minus 1 choose k minus 1. So I believe we're going to replace this with this minus that. That's one thing that's going to happen. So one of them looks like, we're also going to have to drop, like, we're going to have to drop one of these terms, like, we'll remove the k equals 0 case in a minute. Yeah, I just want this to match up, right? What I was saying was if it was n minus 1, I would have been very happy to have this here. So I want to make it look instead like n minus 1 minus k. And I can't just do that. I have to also add kh at the same time, you know? Oh, wait a minute. I'm subtracting this, right? So you're actually subtracting kh if you want it to look the same. Because here I added kh to make this happen. So add kh and subtract kh. This is one term. I also have minus this part. And I did this last week. I didn't do it on video. So like I know that this will eventually work out. But I obviously could have done it a little better. Like I'm not saying, this is definitely not the cleanest way to do it. If I had rehearsed this, I could probably do it in 10 minutes instead of whatever I'm doing here. So I haven't absorbed this in yet. This guy's still sitting here, and I just thought it would be helpful to change this. Because now at least like I can do some sort of grouping. I can say like x minus that combines with this to become x to the n minus 1. Not n minus 1, but like x to the n minus k. Okay? Which is closer to what we wanted, I guess. But yeah, very strange. Kind of gory details. Will we succeed? I don't know. Remember, of course, the goal is to make it look like this, but with n minus k. And then this index will also change. But that's about it. That's all we need to happen. Of course, I've got two terms right now, but two big sums. But I don't think I made a mistake, so that's maybe that's good. We'll see. I suppose this 0 term goes away. When you get to n minus 1, do you get n here? No, you get n minus 2. So it still makes sense. Huh. All right. So if I distribute this in, for each one of these terms that I used to have, now I have this guy increasing to x to the n minus k, we added another factor of x minus thing times h. But then we also have, plus this stuff times y minus, y minus kh, which is good. Y minus kh will also affect this guy. It'll bump him up to be k plus 1. Oh, that's where the reindexing happens. Cool. But this one, it doesn't. No, it happens here too, right? It just becomes n minus k. Huh. Very confused for some reason. Maybe I did make a mistake somewhere. Anyway, you can sort of see what I'm driving at. Man, this is pretty ugly. It's funny, the other day I just stared at this for a minute and then I was like, oh, it's this, and I jotted down a line and it was easy. But that's what I get for not getting enough sleep today. I'm also potentially trying to do like too much in the same step here. Like, what am I going to do with this? I ultimately want this to be the one that survives. So apparently this stuff collapses into one term that kind of cancels out, or like this is the last term. This is that k equals n term. Dot dot dot. Yeah, I think this might be the only problem we do today. I'll try to get through the multinomial part too, but I was just going to try to read that. I wasn't going to try and do it myself. But I will finish this part, 36. So like at 0, you're getting yeah, I don't quite see it. Do some terms cancel or something? I'm not seeing it. Anyway, and was this a horrible idea? Maybe I should have left that alone. Like, maybe this was throwing me off. It certainly made it look worse. I should have waited until that was relevant, We can go back if you want. Let's go back for a sec. But anyway, this guy's, we're going to do this trick. We pull them in. So let's just say or, because I'm undoing this trick for some damn reason. I think we do want that though. I think we do want that. I just don't quite. So like this guy times this term. Let's do it this way. I won't do anything yet. I'll just say it's this times x minus n minus 1 minus k h, right? And then we've also got, I'll add it. don't really know if this is right. But yeah, we're multiplying also by y minus kh. Anyway, the reason I did that is that we know this groups, and we know that this guy groups with that. So there's a cleaner way to write this stuff. As x to the, I suppose it's n minus k, and then there's an extra, another sum here, where this stays the way it was, but the y gets incremented to k plus 1. All right, so that's one thing that happens. Now that's kind of like this grouping that I saw in the easy case, right? In the case of going from 1 to 2. I don't remember this being very difficult the other day. It's too bad I threw out my notes, huh? Yeah, I don't think this is not that hard. I don't know why I'm just staring at it. Isn't this almost what you wanted? Almost. Okay, well, I've got to be able to just like change this and re-index, but it's never gonna. I mean, what happens if you just re-index right now? So there's a 0 term that is still going to be there, and there's an n minus 1 term that is also still going to be there. Huh. Alright, fine. But I just kind of wish it looked like that, right? So I almost want to get rid of this first term and see what happens. But then when I re-index, I lose this term. It feels like I'm going the wrong direction. Like, shouldn't I have an nth term? I'm starting to see why he didn't do it this way. I could show you what he did, by the way. Where is it? 36. Oh, cute. He just says, look at 35. Hold on a second. 35 is the one I'm working on. Okay. Cute. I don't know how I'm going to make any sense of the multinomial case. Is that what that is? Yeah, 36 is just prove the following. But anyway, his answer for 35 is like 2 lines, right? This is trivial. He makes this observation and then He doesn't do it my way, but I think I'm still going to see if my way works out. My way is pretty easy when you know what to do, but for some reason I'm just staring at it. But no, he says, for some reason this happens, which obviously I hadn't noticed that. Oh, okay, sure. So, wait, where's the h to the n come from? Oh, because he divided. Yeah, I still don't quite see it, but it must be kind of obvious. The n factorial part is obvious, like he introduced that. Otherwise, that is almost the exact definition. So yeah, I could sort of see it being true. But then because of that, if you divide, sure, you just get this part. And he's saying that's the same. Oh yeah, it is 1 plus hz. So he's just using the binomial theorem. I see. Cute. Wow, that is really slick. But it all kind of hinges on this part being true. Wow, this is a lot easier and faster than what I'm doing. So he notices this relation and then throws it into the binomial theorem, and that's about it. And boom, that's why binomial theorem is still true. For 36, is this maybe like I just need to be more familiar with the multinomial theorem to begin with? Because 36 he has no answer. He basically just says, yeah, look at 35. So it's clear that he's just like saying, you know, this is what you would have in the regular binomial theorem case, so you still have it here in this case. So that's 35 and 36 if you wanted to be completely done with this problem. It all just hinges on, like, this was the definition. And you can see another, well, I guess he divided by h. That's how he was able to start writing it as factorials. Like, if you instead looked at x over h times x over h minus 1 times x over h minus n minus 1, then other than the fact that you had to divide by a bunch of h's, so this is the same as having n factors of h factored out of your denominator, you know. But then the reason he probably did that is that now this is just regular old factorial. So this is h to the n times x over h factorial divided by, it looks like x over h minus, it's got to be n, right? Like that is a cleaner way of writing this finite set of factors. Yeah, n minus 2, n minus 1, n. So n is the one that gets canceled along with everything smaller than that. Minus n plus 1, minus n plus 2, etc. So that's how you write that. And then he's observing that if we, you know, multiply and divide by n factorial, then you're looking at x over h, choose n, I suppose. Sure. And then I forget where he went from there, but I remember it. He was expanding this just using the binomial theorem, right? this formula that you were talking about expanding is this. Anyway, this would give you sum of n choose k, hz to the k. K goes from 0 to n. Oh, I know what he's doing. He's probably looking at, he says take this series and divide by n factorial. Like, he's looking at, I was going to say he's putting it here in like a, yeah, I'm trailing off here because I forget his next line, but he obviously expanded this. We were looking for a formula for this, which is this. So he put it inside of a, fine, I'll just look again. He treated it like, yeah, exactly, like a power series with a factorial in the bottom, like a power series, like a Taylor series, for instance. He was using this jazz again, you know. Anywho, so when you do that, of course, the n factorials cancel, and you get just this part. Like, yeah, there's a Zn there. I was like, why do I want to write Zn? Probably because it's there. But this part would cancel and give you the sum of just like x over h, choose n, times h to the n, z to the n. Which, I mean, I can see how we got this. I'm just a little fuzzy on oh, right. Right. Cool. Good. That's what I was going to say. All right, good. I was going to say, well, then we need n to be x over h, but that's fine. Because it doesn't have to be like an integer. That's always my hang up. Man, I'm so sick of that. I always see like, you know, obviously this can be a real number, but you know, I see like the binomial theorem and I'm always like, oh, make sure that's like a positive integer. But I don't know why I keep worrying about that. It's never an issue. So yeah, this looks an awful lot like the binomial theorem, except that this is not an integer, but who cares? So this would be 1 plus hz to the power x over h is what you'd be looking at. Why do I care about that? Why is that good? Well, we were trying to get a formula. Like, we're trying to get a formula for this top part, and now you're telling me in here he says use 34, like the one that we just, yeah, use 34 meaning like use this fact. So our right hand side, say, looks like this x to the n over h. So we have a formula for the gamma n's, is what I'm saying. We now have a formula for the x n over h terms. They're given by this thing, which looks an awful lot like the Binomial theorem again. Yeah, this is not one of those things where it's like the explanation is done, I'm just still staring at it. So we noticed that this was xn given h, but that alone is not the answer. Right, it's just this by definition. He wanted you to show that you get this binomial theorem behavior. Right. What we do get, if you happen to put it in this series, we notice that it's equal to this. I don't know if you even really need to observe this. Do you? Like this part I get, you need to sort of recognize that this series, because of your observation, gives you this power series. Yeah, I don't know if you need to explicitly notice this part that I boxed off. But in any case, you're here, and these, guess what's kind of bothering me, this just doesn't feel at all like it just doesn't feel like the formula. Right? We were trying to show, obviously, this still. Yeah, it must be just sort of an obvious thing that I'm not getting. These series are equal, and we have formulas for, yeah, but we have formulas for products. That's what's bothering me. Like his referring to 34, 34 is the one that just says if you had like alpha n over n factorial z to n times beta k over k factorial z to k, and when you look at this answer, say like alpha to the, or gamma to the l, gamma l over l factorial z to l, right? Then you have a formula for this. Actually, let's do the nth one. It would be like, say, alpha 0 plus n choose 1, alpha 1, beta n minus, forgot the beta, n minus 1, etc. n choose 2, alpha 2, beta n minus 2, and so on. So I presume that's what he's talking about. But do I just put an x plus y here? Like, what are you multiplying by? In the previous problem, he just put an e there, so he would just do like, you know, e to the z times this. So that it wouldn't actually change anything. Like when you multiply these, you just have a 1 in every spot. So I'm wondering if he's saying to do this. You know, like somehow I think I'm making it much more complicated on myself. So yeah, what he said was, we got that. Therefore this happens. Fine with that. And then he says apply 34, which he didn't say 34.1. He said this part. 34.1 is actually the one where he uses this trick with the e to the z. But like, what is the product that you're talking about here? And if I do use x plus y upstairs, then that changes this exponent. I think I don't understand this answer. I got the first part, obviously. And I get the second part, but what is that? How does that answer the question? Am I on the right yeah, 35. If you define it like this, you'll have this identity. Which is basically just the binomial theorem. Okay, so this is implying he would have two series. Like, he's saying, if that's the answer that he wants, then he's doing this times y to the n over h, you know. He's definitely taking this product, right? That's how you would get, like, you get a new series, each, you know, we'll call it gamma again, like gamma k over k factorial z to the k. But the formula for this would be the answer that he wants us to prove. The formula for this thing, the nth coefficient would be, you know, x to the 0 h y to the n h plus n choose 1 x to the 1 h y to the n minus 1 h, etc., which is what we're supposed to be. We're supposed to be showing that this equals, that this stuff equals this. I don't know why I wrote that there. It's just a 1. So if you took this product, you get a new product whose coefficients are defined by this. He's telling us that at least the numerator of the nth coefficient is supposed to be this. What? What? Why? Am I just being dumb here? It's not this. Like these are not the same. Wait, this is this? So these are additive? Like, why is that happening? Am I just being... this is... Oh, is it additive because I'm looking at... No, I don't like where you're going with this. My brain. I mean... That's crazy talk. Yeah, that's crazy. That's not what he means. Madness. Yeah, how do you get... Therefore, this happens, and then just apply 34. By apply 34, you mean... So first of all, of course, this is the same as if I had done... Like, this left-hand side is the same as if I had just gone... So maybe you do need this observation that I threw away. It would be the same as this. And then, of course, the exponents add. Ah, you dick. Okay. Yeah, huh. So this product is this series. Like, that's the same, of course, as writing this out. Oh my god, my brain. Choose n, hz to the n, to whatever. The power is x plus, well, the power is actually infinity, isn't it? Because this is a real number. It's not a... So it's the same thing here as well, right? These are infinity. That doesn't matter. It doesn't affect anything. I'm just saying this is infinity. But yeah, anyway. Okay, so that's why it's sort of additive, because it's the exponent on this thing. So this was a super important observation. Otherwise, you can't extend it to this case. But anyway, so these are equal. So this series is the same as this product. I'm losing it. And what? And so what? Well, he looked at this and said it was this. Like, he's also kind of fundamentally saying this series that you're looking at is this. So if you're interested in a formula for the coefficients, so it is true that this is that, but like, I guess that's how yeah, maybe I'm just going the wrong direction. But anyway, we got this. Yeah, I was trying to see a connection between this formula, which we have, we're trying to show is this, and this, the actual thing, the actual x plus y to the n given h thing. This is the connection, I'm pretty sure, but like, I still don't quite get it. This is this, right? So that's all. Okay. Yeah. Oof. Okay. So there was also this observation. So this series is this, it's also this product. And if you write it as this product, you'll see that the coefficients are given by this formula. And hey, look at that. Those are also these coefficients. That's it. Or, put more tersely, apply 34. Apply the evident formula from number 34. When you're looking at a product of two series, power series like this with factorials in the bottom. So a lot like, I don't know what to call those. There must be a nice name for that. I just say it's like Taylor's series form. But anyway, when you take a product of two series that have factorials in their coefficients, you get a new series that also has factorial in its coefficients. But this is the formula that you get out of it for the numerator. His answer was definitely cleaner than my crazy induction tangent that I went on. But yeah, then the multinomial version, he says, notice you can generalize it to a multinomial version. But I'm probably just not that familiar with the regular multinomial theorem. He doesn't say anything about it, obviously. The proof, he just says like, well, yep, look at 35. So it must just be the same. Don't worry about it. Of course, when I did 35, I did not have this cool trick that he did. When I did it, it somehow popped out from staring at these series. Like I just distributed, and I noticed that you can group x with x minus stuff. You can group y with y minus stuff, and that sort of automatically bumps it up. Like here, like what I just wrote over here. And then at some point, I'm pretty certain I used this. And then I did a reindexing, and that was about it. So I'm fairly certain you can prove this with induction as well. but it's a lot of symbols. So let me just make sure that I didn't miss anything. You started with this definition, and by assumption the left-hand side satisfies the binomial thing. So that's that. And then I introduced minus kh plus kh so that I could group them. That puts me here. Okay, for one thing, I guess you'll notice at 0 here, and what about n minus 1? Does it happen there as well? Yeah. There's two terms that are kind of interesting, the first and last terms. What about n minus 1 on this one? Yeah, it gives you x1 and y n minus 1. I feel like something should happen if we pull out the first, like the 0th term on this first guy gives me x to the n, right? Y to the 0h is just 1. X to the n h is a term that you weren't expecting to see, right, unless you were going to this case. So it's like the first sign that we're on the right track. If I don't know, maybe we don't even need to pull it out, but if we get rid of that first term, but then over here I was going to leave it, like here when I plug in 0, I do want to include it from 0, I'm pretty sure. I don't know. Let's see what happens. Pull out the 0th term, you'll get x to the n given h, and then you'll have a bunch more stuff. And then on this other one, I guess I was going to lose the last term, n minus 1, but I'm not seeing why. I'm not seeing how that helps me right now. So we stop at n minus 2 instead, because I'm being a weirdo, doing things that are really not helpful. But I did that because if you plug in n minus 1, here you get x to the 0, and here you get y to the n. So this is the last term, is y to the n. Now, does anything magical happen if you replace one of these with our identity? Or can I re-index now and like somehow it'll cancel? Let's see. If I re-index this one, will it at least match up? If I plug in 0 here, I get n minus 1. If I plug in 1 here, I get n minus 1. So these are the same. So I should really re-index one of these guys, right? I guess this is my target. If we change this to be k equals 1 to n minus 1, you know, at 1, you just get. So I can rewrite this series, for instance, as like k minus 1, right? Yeah, subtract 1 from all the k's and start at 1 instead. This is this now n minus k, right? So these are now indexed the same, and these arguments are the same. The only thing different about them is this, which by our magical formula is the same as... See, it wasn't so bad. I just needed a break. I just needed like an hour-long break from staring at this algebra. So now we're getting k equals 1 to n minus 1, and you're seeing... Is that perfectly clear? Like, well, I'll just write it down. I won't skip any steps. You get that times x to the n minus k h, y to the k h. And this, we have a formula for. That's just n choose k. So you're getting x to the n given h. You're getting the sum from 1 to n minus 1 of n choose k. And then you're getting n minus k given h, y to the k given h. And you have the last term here of y to the n h. And hey, look at that. That's exactly what we were trying to prove. Ta-da! It worked. So yeah, you can do it by induction. He didn't because he's a genius. But I'm not crazy. It does work. I probably confused myself trying to do this early, you know? Trying to use this identity like at the beginning of the computation. But if you pull a couple terms out, right? You pull those nth terms that you like don't think belong there. If you pull those out, suddenly you can like re-index, and then you get that, which looks awfully familiar. So you can upscale that too, and boom, that's the end of it. So that's a formula for x plus y to the n given h. As for why his one worked, I'm not going to do anything new today, I think. But this was 35 again? 35 again, yeah. His answer for 35, for the third time, was to first notice that this would be, well, you'd have to divide by h all over the place, but if you do that, oops, yeah, you get one of these, two of these, yada yada, n of these total, like that, which could also be written, well, with a factorial. Wait, what are you doing? Sure, that's fine. Like that. Right? And then if you multiply and divide by n factorial, that's just a binomial coefficient, right? So his first observation is that this is the same as your, like that's just the definition of the thing that we're talking about. But then he noticed if you make a series using, I guess, these guys as coefficients, all right, then you just be, you know, dropping this in, h to the n factorial, oops, I should have put a k here, should have put a k there, h to the n factorial, x over h, choose n factorial, z to n, right? The h and the n, or sorry, the h and the z have the same exponent, of course, these cancel, so you're just getting the old binomial theorem with an argument of hz inside of it. So this looks an awful lot like, well, so yeah, so this is the same as 1 plus hz to the n, right, to this power. 1 plus hz, not to the n, but to the power x over h is what I meant to say. X divided by h. So he said this is true and this is true. And that was enough to prove the whole thing, because if you looked at this function, it's the same as this product. Which is, of course, this product. I don't know. I realize I just said this. I'm just trying to see if I actually understood it. Just repeating myself to see if I have any idea what on earth is going on. You know how it is. But yeah, this is this product, but this is also the same as this series, right? Right, by the same arguments, yada yada yada. But like this is this, therefore this is x plus y to the k given h over k factorial z to the k, right? And it's also equal to this product. So a formula for, say, the nth coefficient of that series on the left would be given by whatever formula you might have for the nth coefficient of a product of series like this, which in our case is, x to the, you could do nh plus n choose 1, x to the n minus 1, h, y to the 1, h plus n choose 2, x to the n minus 2, h, y to the 2, h, yada yada. Yeah. Alright, so it wasn't that bad. Well, if you know the answer, it's not bad. Yeah, I wasn't going to do more today, but these do look interesting. And I don't know how to do them. Oh, I did look at 37 before, so let's talk about that one. I can handle 37. 38, I'm not going to know. I don't think I'm familiar with that one. But 37 I'm pretty sure I can handle. So 37 I would not have gotten if I hadn't looked at the answer. But now that I see it, like these numbers out front, like there's a 2 on the second term and a 3 on the third term as a coefficient, you know? They're almost like powers. It's almost like someone used the power rule to get them. So that's a hint, I suppose. You think I'm going to be able to reconstruct this thing? It's got to be the derivative of some binomial thing, right? Like, if those numbers weren't there, if all you had was the alternating bit, is that 1 plus x? Like, let's see. it's finite. That's my problem. I was gonna say like 1 plus x to the negative n, but that doesn't feel quite right. I mean, could we just do this? Right? And plug in 1. So for instance, oh, at 1, yeah, at 1 you get 0. Of course, you're right on the boundary here. Like, you're right at the edge of the radius of convergence on this function, I'm pretty sure. But is that true? It's been a while since I checked it. Yeah, I don't know. I haven't looked at this in a long time. The absolute value of that would be 1, and this guy just cancels to give you x. This is, of course, I know this is super basic stuff, I just... So anyway, the ends are gone, you're getting like this. So there's an extra term there, and there's an extra term here. So we're getting n minus k over k plus 1, evidently. Yep. Okay, and we're taking the absolute value of that. So yeah, I guess it didn't affect anything. Anyway, at 1, we're getting 0 is this alternating business, you know, like n choose 0 minus n choose 1 plus n choose 2, da 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 da, like that. Agreed? Which I'm sure was like one of the first things we proved. Oh, he didn't have us do that. We did something similar. Yeah, we didn't actually prove that, but well, we kind of did, right? Because if you let r equal n here, yeah, if you let r equal n on the right hand side, you get something like n minus 1 choose n, which I presume is supposed to be 0, right? Although, what do you actually get if you use the formula? I never thought about this. You're gonna get something crazy? You're getting n minus 1 minus n. You're getting negative 1 factorial. Cool. Okay, well, anyway, those are my little side random thoughts. But my thought was you should probably differentiate this and an n will come out, right? So if you believe this formula, you could certainly take a derivative of this. And you'll get, I guess you're getting a negative? Yeah, you are. Okay. Well, other than the negative sign, on the inside here, we're getting like k x to the k minus 1, which we could reindex. We could rewrite this as, let's see, at 0 you sort of get 0. Like if you looked at this old term, there was probably a 1 there, right? Yeah, you get like 1 minus x plus n choose 2. Well, not x, but nx is what I should have said. So the first term now we're getting is n. But anyway, you could start at 1 if you want. And I guess, are we going to end it? Oh wait, I didn't want to start at 1. I actually want to start at, I want to reindex and start at 0 again. So we're starting at 0, but the first term that you actually see is 1. So we're reindexing everything. You get something like this. And this is k plus 1, x to the k. And yeah, I just shifted everything back by 1, so this is now n minus 1. And since as a derivative, it's the same as this. Which again, I suppose you could plug, like here when we plug in 0, you're getting a negative for the first term, which we probably didn't want. Yeah, probably not. But we don't mind n choose 1 being the first term that we start with, but he wanted to be positive. So I'm going to multiply by negative here, and I'm getting this statement. And we got a negative to the k, and then we have k plus 1 as a factor, and you go from 0 to n minus 1. But this guy has not changed. This is still n in the numerator. And now if you plug in x equal 1, you're getting 0 equals well, they made a little point here. Like if n is 1, then yeah, this is just gone, and you're getting well, you're getting 0 to the 0, first of all. But if n is 1, back here, the derivative of this is negative 1. Right? So this formula, it's fine, but you get negative 1 equals the stuff. I'll come back to that. If n is not equal to 1, then when I plug in 1 here, I get 0, and 0 equals, yeah, we're probably done, right? Yeah, when you plug in n minus 1 here at the bottom, the last term you get is n choose n. And other than that, there's this extra term. It's like 1, 2, 3, all the way up to n. You can see that matches up at n minus 1. So we do get this junk, the formula that we're trying to prove here. So we get 0 if it's not equal to 1. If it is equal to 1, that's kind of strange. Oh, you're probably only getting 2 terms. Okay, good. On the right-hand side, if n is 1, I thought we would get -1, but on the right-hand side, oh, you don't even get 2 terms, do you? Because it was 1 minus x. The derivative is -1. And on the right we have actually this is true no matter what x is, right? On the right we'd still have like 0 to n. Well, I took a derivative, so I guess it's n minus 1 now. If you want to use this formula, you would have something like the 1 term. It's kind of strange. Of 1, choose. You'd have this. Yeah, wild stuff. So at 0, you're just getting 1, 1, 1. 1, choose 1. I guess you're getting some freaking nonsense. Did I miss a negative sign? Is that what happened? Well, on the original function, you had 1 minus x, which of course at 1 is 0. I then took its derivative and I got -1. I wonder where I'm going with this. Maybe if I was a little more careful, it would have worked out correctly. We started with this. 1 minus x is 1 choose 0 minus 1 choose 1 times x to the 1, right? If we differentiate, you just get -1 equals -1 and all is right with the world? Oh, duh. Yeah, no. Of course for n equals 1, you just get 1 for this formula. All right, cool. So yeah, there's 1 choose 1. If you multiply by negative. Yeah, it doesn't really have to do with the formula anymore. It doesn't really have to do with this function anymore. I mean, you can use the function again, but it's probably easier to just say, oh, look, that's 1. And we only have the 1 term. So 38, I don't know. 38, the question says, if you take, it's sort of like the same thing, but with a harmonic series. So I'd imagine it involves integrating. That would be nice, but I don't know. Equals this partial sum of a harmonic series. That's what we're trying to prove. I don't know it. Well, I think I did look at the answer last week, but I don't remember it. I didn't really like spending any time on it. But obviously, if you integrate, if you use the power rule, you'll get something like that, right? So are we able to, would I be able to just take this and integrate it? You don't mean x, you mean so here I'll get 1. Other than this first term, huh? What if I took what is this? 1 plus x to the n, right? So what if I took 1 plus x to the n and subtract 1 off from it so that I don't have this term, and then I integrate? Right? So you're basically getting k equals 1 to n. So it does match up with our series a little closer. Then integrate. Alright, so suppose I integrate this. That is the same as this series. Let's start at 1 again. And choose k, 1 over k plus 1, x to the k plus 1. And it's alternating. So I can fix that by making this a negative, right? So instead we'll look at this guy. Fair enough. And then I guess we could integrate. Like I just want to plug in 1 effectively. So we could integrate from 0 to 1. This is continuous. Is that almost right? What happened to my 0 term? Oh, I got rid of it. Because now am I wishing it was there? Because that 1 is something, like my thing's off. I don't care about the power, but I do care about this number. I had wanted n choose 1 to be the first thing you see. I don't like this negative sign. It seems to be off by 1. So is it the negative of this? Fine, whatever. And then, but this power is wrong. How did I screw up the power somehow? Yeah, it's off. It's off every time. Huh. Isn't it like off by 1? Grrr. scale it. Okay, what if I took this and divided by x? If I subtract 1 and then divide by x, you have a 1 here. You have an x here, which I integrate, and then it matches up. Okay, okay. So this is now an improper integral, but whatevs. The subtracting one is a lot like ditching the 0th term, and then I scaled it back. Okay, okay. Then I scaled it back, and then I integrated it. So we're still doing this, but now right, now these used to be x to the like k minus 1 before you integrated it. So it integrates out to be 1 over k. I imagine this is the same. I didn't actually change the sign. Getting something like that. Which is what we wanted. Or is it? No, you actually want this negative sign to be the other way around. I realize we can just negate that, but did I get it wrong? So this series is like 1 before the division by x. I mean, we had 1 yeah, this is the first power of negative x times, isn't this times n though? Should look like that. So minus nx plus n choose 2 x squared minus da 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 da. And since this is a positive power, just a positive integer we're dealing with, we're going to end up stopping at negative 1 to the n, x to the n. So it's this that I'm saying, subtract 1 from this, and then divide by x, and you're getting, damn it. Okay, so we are going to negate it. We should negate it at the beginning, because I'm getting the wrong sign on, you know. So we'll take the negative of this function. So we'll take like 1 minus x to the n over x. And if you integrate that, you shall get an extra negative sign, which will be just enough to change that, you know. Alright, now it matches up finally. When I plug in 1, you get the first term, which is positive, n choose 1. Like I'm saying, this gives you n choose 1 minus half n choose 2 plus a third n choose 3, da 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 da. Apparently stopping at negative 1 to the n plus 1 over n times n choose n. That's it. That's it. Cool. So that's our left-hand side finally. I'm supposed to show that this equals a partial sum of a harmonic series. That's going to be some magic. So this last part is so I was able to represent this left-hand side as this integral. If you do a u substitution, right, then this is the same as the negative of 1 to 0. So I'm just going to go back 0 to 1 again. But then when we do the substitution, we get 1 minus u to the n over, it looks like 1 minus u downstairs. Which is it does look a lot like 1 plus u squared, etc. We're also kind of away from 0. Right, it's just right on the edge. So we could do log this, but then does that help us? Like, I was just noticing this is obviously, especially since this is a small number, right? Or it's a number between 0 and 1. It's the same as doing this. But that doesn't quite give me, oh, it does. It does give us what we want. It gives us 1 plus half plus a third, all the way up to 1 over n. Cool. That was 38. Ladies and gents, I survived 38. All right. I think I'm gonna call it a day there. Thank you for watching, lads and lasses. Thanks for tuning in, and have yourself a great day.